Hello ladies and gentlemen, and welcome to the next part of this episode. This is the last slide from the previous part, just to remind you where we got to. So let's just overview what we've seen so far. We have that protons and neutrons bond together via the superposition of their threads, and it is this superposition that relates to the strong force or nuclear binding energy. Also, because the electromagnetic fields of the threads exist at 45 degrees to the plane of the rings, the protons and neutrons sit at right angles to each other. Thus, helium-4, which contains 2 protons and 2 neutrons, forms a complete box. We've also introduced the concept of metastates, which exist when there are different ways of fitting the protons and neutrons together, as we saw with hydrogen 3. Lastly, we mentioned that these rings are not fixed structures, but do have some elasticity to them, allowing them to bend and bow depending upon what they're attached to and the repulsive force between the protons. Also, we previously showed you the bottom left-hand diagram of helium-4. However, to make it clear where all the protons and neutrons are located in heavier elements, we're going to be using squares instead of rings. Thus, helium-4 would be represented by the right-hand diagram, but we must keep these ring-based structures in mind, as they are what the protons and neutrons actually look like. Again, just to remind you that we use red rings or squares to represent protons and blue for neutrons. So let's start off with the next element after helium, which is lithium, and in particular we'll be looking at lithium-6, shown in the top 2 diagrams, and 7, the bottom diagrams. These are the 2 stable isotopes of lithium, and for these we've shown you the actual ring-based structure as well as the more clear square-based representation. So let's have a closer look at lithium-6 for a minute. Well, this is our standard helium-4 box, and what we've got underneath is a proton-neutron roof, as we refer to them. For short, we will refer to these proton-neutron roofs as PN roofs. And just to be clear, the P stands for proton and the N for neutron. Thus, this PN roof is essentially a hydrogen 2 nucleus of a proton and a neutron. So these are just bonded on the top or on the bottom of the box, a bit like a roof on a house. Lastly, as proton-proton bonding is not allowed, at least for a stable structure, then this PM roof must be connected to the 2 neutrons within the helium-4 box. Also, for stability, both the proton and the neutron within this roof must be bonded to the respective neutrons within the box. Otherwise the roof would break off, resulting in 2 separate nuclei. Now, moving on to lithium-7, which is shown in the bottom 2 diagrams and contains 1 more neutron than lithium-6. Again, we've got the standard helium-4 box, but this time on the top we've got a hydrogen 3 nucleus of a neutron-proton-neutron. For short, we will refer to these neutron-proton-neutron arrangements as NPN hats. In lithium-7, the NPN hat could be connected to the protons or the neutrons within the helium-4 box. However, for best stability, neutrons should always be connected to protons if possible. Also, again, both of the neutrons within the NPN hat need to be bonded to the box for complete stability. Otherwise, again, the 2 parts, the hat and the box, would break away from each other. So here we've shown you a couple of the basic building blocks that can just be connected together to form heavier nuclei, in this case lithium-6 and 7. Also, you might be asking, how can we connect these hats and roofs to boxes, as the rings do not connect at 90 degrees to each other? Well, as I mentioned in the previous episode, these rings are not rigid structures, they are elastic. Thus, they are able to bend and flex, allowing neighbouring rings to bond together as shown. It just requires more energy to do this. Hence, if we take lithium-7, then the bonds between the hat and the box structures are not as strong as those within the hat and box structures themselves. So what about some other structures? Well, here we show you the nuclear arrangements for all of the even elements, starting from helium and going all the way up to calcium. As you can see, all that we do is just add another helium-4 box on top, creating columns. So carbon-12, for example, is a column of 3 boxes. Oxygen is a column of 4 boxes, all the way up to calcium, which is 10 boxes tall. The only thing to note here is that beryllium-8 is not stable, and this is because single columns containing only boxes can either just be 1 box high, or they must be between 3 and 10 boxes high to be stable. Beryllium-8 being 2 boxes high, alpha decays, i.e. its 2 boxes break apart from each other, because the box is such a strong object. Otherwise, an argument could be made for why doesn't a proton get ejected, converting beryllium-8 into lithium-7, i.e. a box with an NPN hat on the top, as we saw on the previous slide. However, I should point out that columns of 2 boxes with another appendage attached to them, for example an NPN hat, are stable. It's only a column of 2 boxes on their own that are unstable. As I've just mentioned, beryllium-8 is unstable. It's actually beryllium-9, which is the stable isotope, as shown in the diagram. Now this is the first structure we've shown you that actually has an appendage, i.e. hat or roof, attached to both ends of the box or column, which is perfectly fine. So we can see that this contains a standard helium-4 box in the middle, and a PM roof on the top, and an NPN hat on the bottom. Furthermore, we would point out that beryllium-9 could not contain 2 boxes with a neutron lid, i.e. a neutron that covers one end of the column, for 2 reasons. Firstly, beryllium-9 is stable, and as we've just mentioned, a column of 2 boxes is unstable and alpha decays. Secondly, neutron lids are not a stable appendage either. They quickly get ejected, which would again leave us with beryllium-8, which then just breaks down into 2 helium-4 nuclei. This attachment of appendages, for example NPN hats to columns or boxes, can create stable structures, as shown here for hydrogen-3 right through to potassium-39. All of these are stable, and again we see that there is a distinctive pattern as we move through the elements. Also, I should point out here that some of these columns we've attached the NPN hat to protons, for example on lithium-7, whilst on others we've attached the NPN hat to neutrons, for example on boron-11. This is purely so you can see the hat arrangements and the pattern being created. In nature, these NPN hats are more likely to be connected to protons, because this increases stability of the neutrons, since the more protons a neutron is connected to, the more stable it is. After all, remember, a lone neutron is unstable. More information on how protons stabilise neutrons will be discussed in a later video. But for now, we've got this clear and consistent method for producing heavier elements. All we're doing is just adding an extra box on, going from one to another, all the way through these odd elements. Now, there is nothing stopping us sticking a proton into any one of these hats at the top and produce a full column element, so we can clearly see how one element can help to produce the next one and so on. Conversely, a neutron could also be added into one of these hats, which then later decays, producing a proton and creating a full column element. This is the end of the video, but this episode does continue in the next part, so I hope that you will actually join us for that. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.